Hi guys. In the earlier unit, we had found zeros of a polynomial, but the difference is that we were given a zero to begin with, and we had to use that information to find the remaining zeros. Today we are just gonna start from scratch. Okay, we're gonna be given the polynomial, but we're not given a zero to begin with, so that is the difference. Okay, so the directions read, use the rational zero theorem to list all the possible rational zeros, then find all zeros exactly. So the reason why we said exactly is because I want you to list the rational, irrational, and imaginary zeros. Okay, let's do this. So let's talk about the rational zero theorem. So the rational zero theorem says this: if we have a polynomial with integer coefficients, then every rational zero is of the form p over q. Okay, so that kind of makes sense, because what is a rational number? A rational number is a number that can be written as a quotient of two integers. Okay, the books will say a over b. So the rational zero theorem states that if this is your polynomial, then every rational zero is of the form p over q. But what is p and what is q? P, oh sorry, we have a friend. Okay, so p represents factors of the constant term. So in this case, we want factors of the constant term, or a0, and q represents factors of the leading coefficient. I don't want you memorizing, oh yeah, p is factors of a0 and q is factors of a. And no, remember it in words. P represents factors of the constant term, and q represents factors of the leading coefficient. So let's do this. So we have a polynomial, and we're asked to find all the rational zeros. But before we do, we are asked to list all the possible rational zeros. So let's go ahead and write the p over q. Every rational zero is of the form p over q, where p represents factors of the constant term and q represents factors of the leading coefficient. So we want factors of the constant term, namely 4, and then over q, which is factors of the leading coefficient, which is 3. So integer factors, or factors of 4, are 1, 2, 4, but we want to list the integer factor. So it's going to be positive negative 1, positive negative 2, positive negative 4. Cool. And that's all over q, factors of the leading coefficient. Leading coefficient is 3, and factors of 3 are 1 and 3, but we want integer factors, so we're going to say plus or minus 1 and plus or minus 3 to save time. So I know that this is a contradiction to, like, oh, I thought you said you don't want us to submit the answer with the plus or minus. Well, these are not the zeros, so it's okay to list them. Else, if we don't put plus or minus, we're going to have a very long list. We're going to have 1, 2, 4, and then negative 1, negative 2, negative 4. We have no time for that. So let's go ahead, find all the quotient possibilities, and we'll simplify if needed. So the possible rational zeros, we're going to take the top factors and divide it by 1, and then we'll take the top factors and divide it by 3. So let me go ahead, circle this for dramatic effect. So we take all the top factors and divide it by the first factor that we see. So it's going to be 1 over 1. The next one is 2 over 1. We're still not done with the 1. The next one is 4, and then still over 1. We're done with the 1, so we're good. So now we're going to go ahead, take all the top factors and divide it by the next one, which is 3. Okay, this is in my way. Okay, so that will give us a positive or negative 1 over 3. I don't know why I changed the ink. I thought that was black. Positive or negative 2 over 3. And then positive or negative 4 over 3. Okay, and as you can see, we can simplify some of these quotients. So let's go ahead and simplify. So the possible rational zeros are going to be positive or negative 1, 2, 4, followed by those rational, followed by these fractions. Well, they're all rational numbers. You know, a rational number is any number that can be written as a quotient of two integers. In English, it's any number that can be written as a fraction. Okay, so we have a grand total of how many possible rational zeros? 1, 2, 3, 4, 5, 6 times 2. So we have a total of 12 possible rational zeros. Now we're going to take advantage that we have access to a calculator, whether a physical calculator or the software, and then we are going to see which are the actual zeros. Now to determine if if this number, whatever, or one of these, if these are actually zeros, then when we evaluate the function at our proposed 0, then it should make the function value 0. So we can do it by hand, but we're actually going to use a calculator. Okay, so let's go ahead, use calculator. So what I would like for you to do is to go ahead, erase that. Go ahead, punch in the polynomial. Okay, so go ahead, put y equals, that's another problem, 3x cubed. Again, pause and rewind as many times as needed. Minus 10x squared plus 5x plus 4. Okay, the reason why I recommend that you test out each value is because if you manually write, like if you test out 1, 3 times 1 to the third minus 10 times 1 squared plus 5 times 1 plus 4. I mean, we can do it like that, but it's going to be very tedious very quickly. So what we're going to do is we're going to go ahead, use a table of values. Okay, so it has been entered. Let's go ahead to our table. Second table. If you have a list of numbers written automatically, let's adjust your table settings. So gentle reminder, second table set, and then we want the independent variable or the x to be on ask. Okay, so hover over it, hit enter, then you come back. If you have values entered, then go ahead and erase them. Hit the delete button so we can start off fresh. Okay, so let's go ahead, do our xy table. Okay, and then we are only gonna write down in our table the actual zeros. Okay, so if a proposed 0 is a 0 of the function, then when we evaluate it, it should give us a 0. Okay, I don't know if that makes sense. So I want to know, is 1 a 0? I don't know. Let's see. Let's enter it and see if the function is 0. Nope. Okay, 1 is not a 0. Why not? Because when we substitute a 1 for x, that doesn't make the function 0, or the function value is not 0. Is -1 a 0? Nope. How about 2? Nope. How about -2? Nope. Okay, I'm starting to get nervous. How about 4/3? Yes. Okay, let's go ahead, record that. So 4/3 equals 0. Okay, 4/3 is a 0, and then I was gonna write some stuff, but I think I'm gonna test out the rest. The question is, do we really have to test out the remaining possibilities? The answer is no, but you know what, if you want to save some time, I would recommend you test out the rest. Why? The degree is 3, so we're expected to have 3 zeros. Wouldn't it be nice if all 3 zeros were rational numbers? And if they are, then we don't have to do more math aside from this. Okay, so where were we? We tested out 4/3. I need my finger here. Then we're gonna test out -4/3. Nope. How about 1/3? Is that a 0? Where am I? Why do I have 4/3 here? Okay. Oh, I know why. I need my fingers everywhere, because 4/1 is not magically 4/3. Okay, 4/1 is just 4. Okay, so I tested 4/3 prematurely. Okay, so let me go ahead and test 4. I should restart the video, but it's okay, I'm a human. Is -4 a 0? No. Is 1/3 a 0? I think we already tested it, but I don't see it. Okay, so I'll test it again. Is -1/3 a 0? Nope. Okay, how can we tell? Because the function value is not 0. Is 2/3 a 0? So 2/3. Nope. Okay, is -2/3 a 0? Cool. No, it's not. Is 4/3 a 0? It is, because I tested it by accident. Okay, but I'm gonna pretend like I'm surprised. Is 4/3 a 0? It sure is, so we lock it in. Is -4/3 a 0? I think we tested that one by mistake. No, it's not. Okay, cool. So let me hide this. Okay, so the degree is 3, so we're expected to have 3 zeros. I was hoping that all 3 zeros were rational numbers, but they're not. Only one of them is. So the remaining 2, they're gonna be either irrational or non-real. So let me go ahead and write down the facts. So we know that when we evaluate the function at 4/3, that gives us 0. So that's going to lead to that 4/3 is a 0. Now, if 4/3 is a 0, what would be the corresponding factor? So after we subtract 4/3 from both sides, that's going to give us x minus 4/3 equals 0. So we want to tell the world that x minus 4/3 is a factor of the polynomial. Okay. So if 4/3 is a 0, then x minus 4/3 should be a factor of the polynomial. So what are we going to do? We know that 4/3 is a 0, okay? So that means that this is a factor. But we want to confirm it again, okay? That's the only way we're going to find the additional zeros. So in this case, we're going to take the polynomial and we're going to divide it by x minus 4/3. And we want to confirm again that it indeed is a factor. How are we going to do that? We're going to use synthetic division, okay? So synthetic division is a shorthand when we're dividing by a binomial of the form x minus a number. Our book uses r, okay? A lot of books use x minus a, okay? So synthetic division is a shorthand when we're dividing by a binomial of the form x minus a number. So in this case, that number is 4/3. So let's go ahead, prep this up for synthetic division. Okay, give me a sec. Okay, so we do the division box. Outside the division box, we're going to put the value of r. So value of r is 4/3. Inside the division box, we put the coefficients. So from an earlier unit, you know that I like to put the degrees. Right, too big. Let me zoom out. Okay, so the degree is 3. So when we highlight the degrees, we need to have an x to the third, x to the second, x to the first constant. Let's extend the division box. We'll separate the quotient from the remainder, and with confidence put the coefficients of the polynomial that we're dividing into. So the coefficient of the degree 3 term is 3. Coefficient of the degree 2 term is -10. Coefficient of the x term is 5, and constant term is 4. Okay, so let me go ahead, zoom in now. I don't think we're gonna need that anymore. Okay, fantastic. Oh no, that's not the zoom in button. Okay, so for synthetic division, we're gonna bring down the first number and then we're gonna multiply and add all the way. Okay, let me go ahead, bust out my fingers. Product of 3 and 4/3 will give us 4. When we take our time, the sum will give us -6. Next product of -6 and 4/3 is -8. Sorry, that's how I was thinking out loud. And that sum will give us -3. I'm going to try to put a link to earlier videos like synthetic division and factor theorem and all that good stuff. Okay, so next product of -3 and 4/3 will give us -4. And then that sum, tears of happiness. Okay, sum gives us 0 as expected. Okay, why do I say as expected? Because we had said that x minus 4/3 is a factor of p of x, and if it is indeed a factor, when we divide, the remainder should be 0. And again, you can check out the video on the factor theorem, okay, and the remainder theorem and all that good stuff. Okay, so let's go ahead, begin to write this polynomial in factored form. Okay, so where am I? So we have the polynomial that we divided by x minus 4/3, and we're gonna multiply it by the resulting quotient. Okay, so since we divided into a degree 3 polynomial, the degree of our quotient should be 1 under, or degree 2. So that should be x to the second, x to the first constant, and again, happy that the remainder is 0. So let's go ahead, write the polynomial in partially factored form. So we have x minus 4/3 times the quotient, which is given by 3x squared minus 6x minus 3. Now, we are asked to find all the zeros, okay? So if a product equals 0, what are gonna be the following zeros? X minus 4/3 will lead to a 0 of x equals 4/3, or to a 0 of 4/3. But yeah, we already knew that. I just wanted to write it out, okay? We had said that 4/3 is a 0. Now this trinomial is gonna lead to a 0 of I have no idea. Okay, so let's go ahead, set it equal to 0 so we can find the additional zeros. Now the question is, should we try to solve by factoring? I mean, you can, but in this case, it's never gonna be factorable. Why not? If it's factorable, then we should have had additional rational zeros, and then we would have caught it when we did the table of values. So no, you solve it by using the quadratic formula, or you complete the square. Students' favorite quadratic formula, so let's give the people what they want. So you can write the formula right now. Well, I want to point out that 3, 6, 3 have a common factor of 3. So let's go ahead, tone down the numbers by dividing both sides by 3. Okay, in my made up math words, I'm going to say reduce the equation, but don't tell my boss that I say that. If you're going to quote me, then tell my boss this. Let's go ahead, apply the division property of equality, and we're going to divide both sides by 3, so that way we can fix it so the coefficients don't have any factors in common other than 1. Yeah, that's like a long way to say it. So bad math, reduce the equation. Again, those are not proper words, but it's okay, you get me. So when we try to tone down the numbers by dividing both sides by 3, that's going to give us x squared minus 2x minus 1 equals 0. Now the question is, what if we didn't divide both sides by 3? It's fine. Your numbers are going to be slightly more inflated, and that's okay too. Okay, so let's go ahead and write down the quadratic formula. So we have x equals opposite b plus or minus the square root of b squared minus 4ac. And that's all over 2a. Fantastic. So for my peace of mind, let me go ahead and identify the values for a, b, and c. Leading coefficient is 1, that's our a. Coefficient of the middle term is -2, that's our b. Constant term is -1, that's our c. So we have the formula nailed. We have a, b, c identified. We have easy access to a calculator, so let's do this. So that will give us x equals opposite b. Value of b is -2. Go ahead, put my finger on it. And then we're going to add or subtract the square root of b squared. Value of b is -2 minus 4 times a. Value of a is 1 times c, which is -1. And that's all over 2a. So value of a is 1. This is our answer. Well, these are our additional zeros. Okay, we got this, guys. We have a calculator. Punch it in or freehand it. Let me zoom out. Okay, so we have that x equals opposite of -2 is +2, and then we're going to add or subtract the square root of whatever this simplifies to. I mean, you can do it by hand, but for the purpose of time, I'm just going to tell you what it simplifies to. When I punch it into my calculator, that gives us 8. Okay, you're going to have to trust me on that. So plus or minus square root of 8 all over 2. Fantastic. So let's go ahead, work our magic, and simplify the radical. It's very hard for me to do it mentally. That's why I always bust out a thinking area. 8 has a perfect square factor of 4, or a nice way to rewrite 8 is 4 times 2. Square root of 4 simplifies to 2, and that will leave us with 2 square root of 2. So let's go ahead, bring it down. So we have 2 plus or minus a square root of 8, which simplifies to 2 square root of 2, and that's all over 2. So in this case, we have a fraction, so I want to ask myself, is it reduced? And the answer is no, because this 2 and this 2 all have a common factor of 2. So let's go ahead, reduce by 2, old school notation, you know, no cross canceling. When we reduce by 2, let's show the reader what we're left with. 2 divided by 2 will give us 1, plus or minus 2 root 2 over 2 will give us the 2's canceled, so that will leave us with square root of 2. Denominator, 2 divided by 2 is 1, but if the denominator is 1, there's really no need to write it, so that will give us just 1 plus or minus square root of 2. So we did it, guys. Let's just go ahead and summarize it. We've initially found that 4/3 is a 0. I can't project it right now, and thanks to our additional hard work, we found the remaining 2 zeros. So the degree of the polynomial is 3, so we're expected to have 3 zeros. 1, 2, 3. So let's get our full credit. So the zeros are 4/3, 1 plus the square root of 2, and 1 minus the square root of 2. So that was a lot. Is this problem going to be on your test? Of course it is. So what we're going to do, we're going to do 2 more problems. I know it's like, yeah, we got it. So is it really vital for us to do 2 more? Well, nothing is vital, but I'm going to make it spicier each time around. So bear with me. I'll be right back. Okay guys, so let's go ahead and knock out another problem. They do say practice makes perfect, so let's do this. So we are giving a polynomial and we are asked to find all zeros exactly. Before we do that, we want to use the rational zero theorem to list all the possible rational zeros. So remember, every possible rational zero is of the form P over Q, where P represents factors of the constant term and Q represents factors of the leading coefficient. So let's do this. Factors of 11. So let me just put P in parentheses. Sorry. Factors of the constant term. Factors of 24 are 1, 2, 3, 4, and I'm not sure if I can list them in order from smallest to largest from rote memory. So what I'm going to do when the numbers are out of my zone, I like to do a factor table, and then we're going to list all the factor pairs in order from smallest to largest. That is the only way that we can ensure that we list them all. So I know that you know that 1 is a factor. So 1 times 24 is 24. Let's go ahead and bust out our prerequisite skills. 2 is a factor. 3 is a factor. And how do we know when we're done? We're done when, if we list them in order, we are done when we already hit a factor that's in there. 4 is a factor. 5 is not. 6 is, but it's already in our list, so we can safely stop. Okay, so now with confidence, we're just going to snake it through. So the factors of 24 are 1, 2, 3, 4, and then we snake it up. 6, 8, 12, 14. Okay, so copying our factor table, we have 6, 8, 12, and I think I said 14, 24. But we want the integer factors. I'm going to go ahead and put my plus or minus notation before them. All right. So we have, I don't know how many factors, I can't count. So then we're going to go ahead, divide them by Q, which is going to be factors of the leading coefficient. Oh, how I love the number 11, because it's a prime number. So it's only going to be factors of 11, it's going to be 1 and itself. And let's go ahead and do this. I know that you can do a lot of things in your head, but I cannot, so I'm gonna write a lot. So let's go ahead, list all the possible rational zeros. So we're gonna list all the possible rational zeros of the form P over Q. So we're gonna take these top numbers and divide it by 1. And then we're going to take these top numbers and divide it by 11. So let's go ahead, divide by what? So again, you can do things in your head, but I cannot. So I'm going to just write it out. So the possible rational zeros, let's do this. We have 1 over denominator of 1. Then we have 2. Remember, we're dividing all the top numbers by 1, followed by 3, followed by 4, followed by 6. So again, the question is, do you have to show like 1 over 1, 2 over 1? No, of course not. You're cool like that. You can just write down the simplified quotients. But I am not cool like that. This is why I need to write it all out. Okay, so we're done dividing the top factors by 1. So 1 has served its purpose. Now let's go ahead, divide the top factors by 11. So it's going to be 1 over 11, 2 over 11. But of course, we want positive or negative quotients. Okay, so we have 1 over 11, followed by 2 over 11. It's like, why am I picking ugly numbers? You know what? Life ain't pretty. Okay, so sometimes I put ugly numbers so I don't have to do as many problems. 4 over 11, 6 over 11, 8 over 11, almost done. 12 over 11, and then 24 over 11. So if this polynomial does indeed have rational zeros, it's gonna come from this list. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 16. We have a grand total of 32 possible rational zeros. Now I would love to box this, but my first I think it was 8. My first 8 I can simplify them, so because I wasn't able to simplify in my head. So here I go. So we want to tell the world that the possible rational zeros are going to be 1, 2, again, we're just simplifying the quotients, 3, 4, again, and their opposites, 6, 8, 12, 24. Yeah, my hand is in the way. Sorry, I forget. Then we have the 1 over 11. And these are already simplified. We can't reduce them. 2 11ths, 3 11ths, 4 11ths. Again, and its opposites. 6 11ths, 8 11ths, 12 11ths, and 24 11ths. Cool. This will be the first and only problem where I give you so many possible rational zeros. So one of the things that we were supposed to do is use the rational zero theorem to list all the possible rational zeros. How many did I say we have? 1, 2, 3, 4, 5, 6, 7, 8, 16. We have a total of 32 possible rational zeros. Now the degree is, where am I? The degree is 4. So we're gonna have at most 4 rational zeros. Hopefully all of them are 0, so that way we can avoid the synthetic division. So technically we're supposed to test them out by hand, but you know what? We have access to a calculator, so I'm just gonna write down from calculator what are the actual zeros. Calculator. Okay, so let me go ahead and do my XY table. Let's go ahead, take out a calculator, and then punch in the function. So remember, pause and rewind as many times need be. Okay, so we're gonna enter y equals, oh, what am I doing? Sorry, I guess I was doing something behind the scenes. So let me go ahead, clear that. So we have 11 times x to the 4th power minus 62 times x to the 3rd power minus 13 times x squared minus 62 times x minus 24. And then we're gonna go to our table of values. So remember, we had just done a problem similar to this one, so the table should be set. Okay, so second table, and these are the values that we tested in the earlier problem. So let's go ahead and delete them because they're in our way. So let's go ahead, test out our 32 values one at a time, unless we get 4 zeros in there. Okay, so the first one that we're gonna test out is 1. Let me go ahead and make this a little bit darker. Okay, cool. Let's go ahead, test out 1. Is that a 0? Nope. How about -1? Nope. All right, how about 2? Nope. How about -2? No. How can we tell that they're not 0? Because if these are zeros, then that will make the function a 0, and no. So let's go ahead, keep testing them. Okay, a lot more to go. Is 3 a 0? Nope. How about -3? Nope. How about 4? Nope. How about -4? All right, so I'm gonna save you my nopes until we get a 0. Oh wait, look, I spoke too soon. Okay, so we have that 6 is a 0. So I guess you can stop and do the math, but again, we already have the table, so why don't we go ahead and test them out. I'm gonna test them out really quickly without saying nope so many times. So -6, 8, -8, 12, -12, 24. That's no. Okay, that doesn't say 0. -24 doesn't say 0. 11. So 1 divided by 11. No. How about its opposite? -1 over 11. No. 2 over 11. No. How about -2 11ths? Okay, not just kidding. How about 3 11ths? 3 over 11. No. How about its opposite? -3 over 11. No. Where am I? Let me put my pen over here. Now we're at 4 11ths. 4 over 11. No. How about its opposite? -4 over 11. Oh yeah. Okay, which one was that? -4 over 11. Let me test it out. Okay, let me put my finger on it. Okay, -4 over 11. Yeah, that one was it. Okay. Also, the degree is 4, so we're expected to have 4 zeros. It would be nice if all of them are rational zeros, so we can avoid the synthetic division. Okay, so sorry, I spoke too soon. How about 6 11ths? You know what? Let me clear this. I just need to see numbers. Okay, fantastic. So 6 11, so 6 over 11. How about its opposite? All right. How about 8 11ths? How about its opposite? 12 11ths? Its opposite. 24 11ths? No, and its opposite. Okay guys, I was really hoping we will have more rational zeros, but no. Oh, I forgot to put a 0. Okay, so the degree is 4, so we're expected to have 4 zeros. The degree is 4, so we're expected to have 4 zeros. I was crossing my fingers and hoping that all 4 of them were rational, but they're not, so I'll take this gift, okay? So the reason why I put this problem is because the earlier problem, we only had 1 rational zero. With this problem, we have 2 rational zeros. So I want to show you what to do when you have more than 1 rational zeros. Okay, so from our work, we have that, let me go write it down. We have that p of 6 equals 0, okay? When we evaluate the function at 6, that gives us a 0. So we want to tell the world that 6 is a 0. Now, if 6 is a 0, then that means that x minus 6 should be a factor. Why? Because, let me just put x equals 6. We'll subtract 6 from both sides, and that will give us x minus 6. Okay, so if 6 is a 0, then that's going to lead to x minus 6 is a factor of the polynomial. So what are we going to do? We're going to go ahead, take the polynomial and divide by x minus 6. What else do we have? We have another 0. Okay, so we have p, the function evaluated at -4/11 is 0. So then we're going to tell the world that -4/11 is a 0. Now, if -4/11 is a 0, then that's going to lead to x plus 4/11 is a factor of the polynomial. I'm running out of space, so I didn't have space to write. We'll add 4/11 to both sides. And after we add 4/11 to both sides, that's going to give us x plus 4/11 equals 0. Yeah, you just have to trust me on it. So we have that x minus 6 is a factor of p of x, and x plus 4/11 should also be a factor of p of x. Well, we know that they're factors because we have that 6 and -4/11 are zeros. But the thing is, we want to confirm it again. Not because we don't trust our math, but that's the only way we're going to find the additional zeros. Okay, so the degree is 4. We have 2 rational zeros. Let's go ahead and find the remaining zeros. So we're going to take the polynomial and divide it by any one of these 2 factors. You could divide it by x plus 4/11, or you can divide it by x minus 6. We're going to divide it by both of these. It's just one at a time. I don't have time to face my fear, so I'm going to go ahead and divide it by x minus 6 first. So let's go ahead and take that polynomial and divide it by x minus 6, but we're going to use synthetic division. So synthetic division is a shorthand when we're dividing by a binomial of the form x minus a number. Our book uses r. Okay, your book may use something else. So we have since we are dividing by a binomial of the form x minus a number, then we can go ahead use synthetic division. So in this case, r equals 6. Let's prep this up for synthetic division. So outside the division box, we're going to put the value of r. Value of r is 6, and then inside the division box, we're going to go ahead put down the coefficients of the polynomial that we're dividing into. We are dividing into a degree 4 polynomial, so we should have a coefficient for x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, constant. Okay, so let me go ahead separate the quotient from what would be the remainder. So it doesn't, I wrote a lot, so I don't know if I can project the polynomial. Okay, so you're gonna have to trust me. Okay, the coefficients are 11, -62, and then you can read the rest. Okay, give me a sec. So hopefully I don't make a mistake in copying. So coefficient of the x to the 4th is 11, of the x to the 3rd is -62, of the x squared is -13, of the x term is -62, and the constant term is -24. So we had already said that 6 is a 0, so that means x minus 6 should be a factor. Let's go ahead confirm it. So the remainder needs to be 0. Okay, it needs to be. Okay, let's pretend like we're surprised when it is. Okay, so let's go ahead begin the process. So for synthetic division, we'll drop down the first number and then multiply and add all the way until we can't. Product of 11 and 6 will give us 66, and that sum will give us 4. Product of 4 and 6 is 24, and that sum gives you I can't do that in my head, a 1 or 11 like normal people speak. Product of 11 and 6 is 66, and that sum is 4. Final product Product of 4 and 6 is 24, and that sum is 0. Oh, I'm smiling because the remainder is 0 as expected. Alright, so let's go ahead highlight the degrees of the quotient. Since we divided into a degree 4 polynomial, the degree of our quotient should be 1 under, or 3. So that should give us x to the third, x to the second, x to the first, constant, and then the remainder is 0. When we begin to factor the polynomial, that will give us p of x equals, we divide it by x minus 6, and then we're going to multiply it by the quotient, which is this right here. Okay, so we have p of x equals x minus 6 times 11x cubed plus 4x squared plus 11x plus 4. Fantastic. Now the question is, what are we gonna do? Well, the degree of the resulting quotient is 3. I don't know how to solve a cubic equation algebraically unless I graph it. So what we're going to do, we're going to look at the next 0, okay? So we had said that x plus 4/11 is a factor. So we're going to take our quotient and divide it by x plus 4/11. So let's go ahead, take our quotient and divide it by, what was it? X plus 4/11. Fantastic. So remember, we're going to divide by using synthetic division. So synthetic division is a shorthand when we're dividing by x minus a number. This is not quite x minus a number, but we can force it. We can write it as x minus negative 4/11. Then we can tell the reader, oh yeah, okay, the number that follows the subtraction sign is negative 4/11, so R, or whatever your book uses, is negative 4/11. Fantastic. So let's go ahead, prep this up for synthetic division. Outside the division box, we always put the value of R. Value of R is negative 4/11. For the top row, we're going to put the coefficients of the dividend, whatever you're dividing into. We're dividing into this bad boy, so the degree is 3. So let me highlight the degrees. We have x to the third, x to the second, x to the first, constant. Yeah, this is in my way. I'm running out of space and I'm trying to save a tree. Alright, so let's go ahead, extend it. We'll separate the quotient from the remainder. And again, this is a factor, so the remainder needs to be 0, else I'm going to cry. Alright, the coefficients of the dividend, or what we're dividing into, is going to give us 11, 4, 11, and 4. So let's do this. So let's begin the synthetic division. We're going to drop down the first number, and then we're going to multiply add until we can't no more. Product of 11 and negative 4/11. Go ahead, use your calculator if need be, but that will give us negative 4. Multiply add, multiply add. Sum of 4 and negative 4, where am I, is 0. Product of 0 and negative 4/11 is 0. Sum of 11 and 0 is 11. Final product of 11 and negative 4/11 is negative 4. We keep our cool, the sum is 0. Okay, so since we divided into a degree 3 polynomial, the degree of our quotient needs to be 1 under, or 2. So we have x squared, x to the second, x to the first, constant, and that's our remainder. So I'm smiling because we had said that x plus 4/11 is a factor, so when we divide, the remainder should be 0. So let's begin to continue to factor a polynomial. Okay, so we took our polynomial and first divided by x minus 6. Then we took our polynomial and divided our result. Okay, then we divided by x plus 4/11. Okay, and then that leaves us with the following quotient. Okay, 11x squared plus 0x, there's no need to write it, plus 11. Ooh, we're done. Okay, well, almost done. Okay, the first factor leads to a 0 of 6, but we already did that. Oh, let me zoom out. Okay, the first factor leads to a 0 of 6, but we already established that. Okay, the second factor leads to a 0 of negative 4/11. I don't need you to write this over. I do this for note-taking purposes. Cool. So, but we already established that there. The third factor is going to lead to a 0 of, I have no idea. So let's go ahead, find out. If you want to know sorry, I'm trying to fix this. Okay, so to find the additional zeros, we're going to take that third factor and set that equal to 0. Okay, so I'm out of space. I'm going to bust out my mental math. When we subtract 11 from both sides, that's going to give us 11x squared is equal to negative 11. To isolate the squared part, after we divide both sides by 11, that's going to give us x squared equals negative 1. To finish it off, we're going to apply the square root property and square root both sides. To undo the square, we're going to go ahead square root, and at this point we'll insert our plus or minus. It's kind of squeezed in, so I'm going to circle it for dramatic effect. On the left side, the square and the square root undo each other, and that will leave us with the radicand of x equals positive or negative, whatever the square root of negative 1 simplifies to. But if my memory serves me correct, isn't the square root of negative 1 the imaginary unit? Yeah, I thought so. Okay, so that's going to give us x equals plus or minus the square root of negative 1, which simplifies to the imaginary unit I. Okay, so we did it, guys. Let's just get our credit. Okay, so the zeros. Okay, the degree is 4, so we're expected to have 4 zeros. One of them is 6, another one is negative 4/11, another one is I, and the other one is negative 4i. So remember, the degree is 4, so we're expected to have 4 zeros. We nailed our 4. Cool. So that was pretty intense, I know, but that way we don't have to do so many problems. So the first problem that we knocked out had one rational zero. I told you how to handle it if you have more than one rational zero. It kind of seems like what to do. It kind of seems like we should stop now, but no, I have another surprise for you, but it will be worth it, trust me. So let's go ahead and do the third and final problem. Give me a sec. Okay guys, so let's go ahead and wrap it up with our third and final problem. You know the speech. We are asked to use the rational zero theorem to list all the possible rational zeros, and then we are asked to find all zeros exactly. So no rounding. We want the rational, irrational, and non-real zeros. Okay, so the rational zero theorem, remember, states that every rational zero is of the form P over Q, where P represents factors of the constant term and Q represents factors of the leading coefficient. So let's do this. So factors of the constant term over factors of the leading coefficient, namely 1. So factors of 5, oh, how I love 5, especially coming from that brutal problem that we knocked out. Factors of 5 are 1 and itself, but we want integer factors, so this is why we put plus or minus before. 1, factors of 1 is just 1 and itself. That's it. So let's go ahead and write down all the quotient possibilities. So we're gonna take the numerator. I keep putting a comma, sorry. Okay, that's a really weird equal sign. So let's go ahead, take the numerator and divide it by the denominator. Next entry, we're gonna go ahead, take 5 and divide it by 1, and that's it. Let's go ahead, simplify our quotient. So quotient of 1 in itself is 1. Quotient of 5 in itself is 5. Okay, so we have a total of 4 possible rational zeros. That's a relief coming from the list of, what was it, 32 that we had. I already lost track. So let's go ahead, use a calculator to test out. So use calculator. Sorry, I need to say it like that in order for me to spell it. Okay, so let's go ahead and use a calculator to test the possible rational zeros, and then hopefully we have at least one. So the degree is 4, so we're expected to have 4 zeros. Wouldn't it be nice that all 4 of them were, all 4 rational zeros were a 0? Yeah, okay, sorry for like extra words. That's what happens when you get nervous. Okay, so let's go ahead and enter the polynomial function. So we're gonna go to y equals, let's go ahead and clear that. So we have x to the 4th plus 4x cubed. And I keep forget to verify my polynomial, but I mean you should always check it. But these kinds of problems can get ugly very quickly. Okay, so we just do a double check. Yeah, I typed it in correctly. And then we're gonna go to our table values. So remember, second table. So I'm trying to zoom out. So we're gonna do second table, and then this is the work from the earlier problems. Let me go ahead, delete it, and let's go ahead, test out our 4 possible rational zeros, starting with 1. Is 1 a 0? Oh yeah, I know it's not. Is -1 a 0? Yes. Okay, So -1 is a 0, and then we'll put the speech in a bit. Okay, how about 5? Is 5 a 0? No. Is -5 a 0? No. Okay, so in this case we have that -1 is a 0. So let's just write that p of -1 is a 0. When we evaluate the function at -1, we have that the function value is 0. So that means that -1 is a 0. Now, if -1 is a 0, what will be the corresponding factor? When we add 1 to both sides, that's going to give us x plus 1. So we want to tell the world that x plus 1 is a factor of the polynomial. Okay. So again, -1 being 0 leads to a factor of x plus 1. So what we're going to do, we are going to take the polynomial and divide it by x plus 1. Okay, so let's go ahead and take our polynomial and divide by x plus 1. In this case, we are going to use synthetic division. So remember, synthetic division is a shorthand when we're dividing by a binomial of the form x minus a number. So I always say x minus a number because depending on the book that we use, they'll say R, A, I think that's it. Okay, cool. So we don't have x minus a number, but we're going to force it. We're going to write x plus 1 as x minus -1. So we're still dividing by x plus 1, but in an undercover format. So now in this case, when we write the addition problem as a subtraction problem, then we can more easily see what is the value of r, or what is the number that follows the subtraction sign. So when we use synthetic division to divide by x plus 1, let's go ahead and prep this up. We'll do our division box. Outside the division box, we're going to put the value of r, which is -1. Inside the division box, we're going to put the coefficients of the polynomial, or the dividend. Okay, so the degree is 4. You know my style. I'm going to highlight the degrees. So we should have an x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, constant. Okay, let's go ahead and do this. So the coefficients are going to be 1, 4, 10, 12, 5. So we didn't need any 0 placeholders. Okay, this is too low, and let me go ahead zoom in. So let's go ahead separate the quotient from the remainder, and let's go ahead do the math. So for synthetic division, we're going to bring down the first number, multiply, add until we can't no more. Product of 1 and -1 is -1, and then that sum will give us 3. Product of 3 and -1 is -3, and that sum is 7. Product of 7 and -1 is -7, and that sum is 5. Final product of 5 and -1 is -5, and the sum is 0. So we had divided into a degree 4 polynomial. So the degree of our quotient, our answer should be 1/3. So we should have an x to the 3rd, x to the 2nd, x to the 1st, constant, and then the remainder. Now we had said that x plus 1 is a factor. So because it's a factor, when we divide, the remainder should be 0. So we did it. So let me go ahead begin to write the polynomial in a partially factored form. We had just divided the polynomial by x plus 1, and when we did, we're left with the following quotient. Okay, we're left with x cubed plus 3x squared plus 7x plus 5. Fantastic. So x plus 1 will lead to a 0 of -1. This cubic expression will lead to a 0 of I have no idea. Okay, so the question is, in the earlier problem, I put it away. Okay, where was it? Okay, the reason why we divided again is because of what we had. I mean, I don't know how to do this, so I pretty much want to tone down this this quotient until we have a degree 2 polynomial, so then we can solve it by quadratic formula or whatever technique we have. Okay, so coming to this problem, that is not a degree 2 expression, so I cannot use the quadratic formula or any other technique. But I'm at a loss because we have no more rational zeros. Okay, so there's a reason to my madness. There's a reason why we're doing a third problem. It's because I want to cover all case scenarios. What we are going to do when we're at a loss for numbers, so we can't tone it down to a degree 2 polynomial, we're gonna go ahead examine the graph of the polynomial and look out for any even multiplicities. Okay, so let's go ahead take out a graph. We already punched in the polynomial. Okay, we already punched in the polynomial because that's how we were looking at the table of values, but you can confirm. Okay, let's go ahead look at the graph. From our work, we have that -1 is a 0. Let's see how the graph behaves at -1. So let's go ahead, hit graph. Okay, that's not what you should have. Apparently I was doing something else. So let me go to the standard viewing window. So zoom 6. What happened? Okay, so we had already set that -1 is a 0, but remember what we talked about in earlier video, zeros with even or odd multiplicity. If the graph intersects the x-axis, then we have a 0 with odd multiplicity. But if the graph is tangent to the x-axis, then the multiplicity needs to be even. So like a tangent, it's just code for it touches at one point. In English, we kiss and go. Okay, so let me go ahead, take a screenshot of what we have. Okay, we have x, that's the y-axis, and that is -1. Do you have to do this for credit? Well, not for credit, but I do recommend. Okay, so let's speak to ourselves. So graph is tangent at -1. Okay, if the graph is tangent at -1, then the multiplicity has to be even. Okay, multiplicity is even. Okay, we're gonna go for the minimum degree, so we're gonna say 2. Okay, so in this case we had divided by x plus 1, but if -1 is a 0 with multiplicity 2, check it out, we're gonna divide by x plus 1 again. Okay, so let's go ahead, take our quotient and divide it by x plus 1. Why? Because the first time around is because it was -1 is a 0. The second time around is because -1 is a 0 again. Okay, with multiplicity of 2. Okay, so let's go ahead, take our quotient. So the degrees are 3, 2, 1, blast off. Okay, let's go ahead, put down the coefficients. So 1, 3, 7, 5. It was easier for me to take it from the synthetic division, but you could have taken it from your polynomial here, whatever works for you. We are dividing by x plus 1, so in this case the value of r is once again -1. So value of r is -1, and let the division begin. Sorry, I forgot to separate the quotient from the remainder. So let's go ahead, bring down the 1, and then we multiply, add until we can't anymore. Product of 1 and -1 is -1, and that sum is 2. Product of 2 and -1 is -2, and that sum is 5. Product of 5 and -1 is -5, and then that sum is 0. We divide it into a degree 3 polynomial, so the degree of our quotient needs to be 1 under, or 2. So it'll be 2, 1, 0, remainder. Okay, the remainder is 0, which makes me happy, because if x plus 1 is a factor, then the remainder should be 0. So let's go ahead, write down the polynomial in partially factored form. So we have that the polynomial, the first time around, we divided by x plus 1, and then we divided by x plus 1 again, because we had said that -1 is a 0 with the multiplicity of 2. And then that left us with the following quotient. Okay, so 1x squared, or x squared, plus 2x plus 5. Okay, if you were to expand this, you will get the original degree for polynomial, but we have no time for that. With your permission, I'm going to go ahead use exponents for repeated factors. So we have p of x equals square of x plus 1, and we're multiplying it by the resulting trinomial. Okay, fantastic. Now, from our work, we have that the square of x plus 1 leads to a 0 of -1 with the multiplicity of 2. Now, let's go ahead factor the result. Sorry, let's go ahead find the additional zeros. So if we want to know what makes it a 0, let's go ahead set this equal to 0. Now, this should not be factorable. If it was, then the zeros are rational and we would have got it from our list of 4 possibilities. So we go straight to quadratic formula or complete the square. Let's give the people what they want. So I don't have a lot of space, so I'm just go straight to plugging in the numbers. Hopefully I did this right. So the leading coefficient is 1, that's our A. Coefficient of the middle term is 2, that's our B. Constant term is C. I'm going to go ahead go straight to the answer. Okay, so we have x equals opposite b, value of b is 2, and then we're going to do plus or minus the square root of b squared, so that'll be the square of 2 minus 4 times a, value of a is 1, b squared minus 4ac, value of c is 5, and this is all over 2a. So 2 times a or 2 times 1. We got this. So let's clean this up. So that will give us negative 2 plus or minus. We punch it in. And the square, and 2 squared minus 4 times 1 times 5. If I punched it in correctly, gives us negative 16. And that's all over 2. Fantastic. The square root of negative 16 simplifies to 4i. Pretend I did a thinking area. Okay, the square root of negative 16 simplifies to 4i. Now, what's going on? Because we have a non-real solution or a non-real zero, we need to put this in standard form for a non-real number, a plus bi. So let's go ahead, take that first term, divide it by 2, and then we're going to add or subtract the second term and divide it by 2. Sorry, this is in my way. Quotient of negative 2 and 2 will give us negative 1. Quotient of 4i and 2 will give us 2i. The degree of the polynomial is 4, so we're expected to have 4 zeros. The first 2 come from negative 1, so negative 1 recycled twice. The third one comes from negative 1 plus 2i, and the fourth one comes from negative 1 minus 2i. So we did it, guys. Let's just go ahead and answer. So we have that the zeros are negative 1, and we need to highlight the multiplicity. If we don't, then we're just going to list 3 zeros instead of all 4. Negative 1 with the multiplicity of 2, followed by negative 1 plus 2i, and negative 1 minus 2i. So I think this was the longest video to date, but I thought it was in your best interest if we had all 3 problems in one video instead of scattered across. Thanks, guys. Until next time.